In this video demonstration, I want to show how we're able to do privacy-preserving proofs within Orbit Enterprise. So at Northern Block, we're currently focused on building use cases which are privacy-preserving, thus best suited for AnonCreds, we feel. And so for those interested, we recently wrote a piece about our learnings from Aries, Indy, AnonCreds, and other credential implementations you could find in the blog section of our website. But with AnonCreds, you could do zero-knowledge proofs. And in cryptography, the zero-knowledge proof is a method by which an entity can prove that they know a certain value without disclosing the value itself, privacy-preserving by nature. And with AnonCreds, so you could do zero-knowledge proofs. So we decided to implement some of these capabilities into Orbit Enterprise, and this is what I'm showing here today. And I'm going to show 4 different implementations of zero-knowledge proofs. The first one being restrictions, the second one being data minimization, the third one being compounding proofs, and the fourth one being predicates. And we're going to show it here through our instant task or instant verification screen. So here I'm going to go and I'm going to start an instant task. And as this 3-star hotel, my request reason is I'm doing a hotel check-in. So the first type of zero-knowledge proof that we're able to do here is a restriction. So I'm able to put a restriction on the schema or on the credential definition. So if I select the credential definition, I could select if I have a specific issue or organization that I want to accept the credential definition from, and if there's a specific credential definition that I want to accept. And so if I go here inside of the credential definition and I select the employee ID, I'll see all of the different attributes here that show up in the employee ID. So I've set this condition, I've set this restriction. So that's the first zero-knowledge proof that I'm demonstrating here today. The second one being data minimization. So perhaps within a credential definition itself, I don't necessarily need to see the department number. I'm doing a hotel check-in. I don't really care about that. I also don't need the head office location. But perhaps I need these other fields here. And so that's the second concept, which is of data minimization. And then it takes me to the third one, which is compounding proofs. So maybe in my hotel check-in, in my policy, I need to verify a government ID as well. So I'm verifying an employee ID because maybe I'm giving a discount to someone that presents an employee ID. They get 10% off on their stay. But I also want to verify a photo ID because I have to do that as well. And on this one, I'm going to select the schema and I want to verify the photo ID schema. I trust this schema. I know it's a schema that has strong governance around it. I know that this schema could only be used in credential definitions that are issued by government bodies. I trust this. So I'm going to select this one. And I have the 4 fields selected here, and maybe this allows me also to compare, does the first name, last name match on the employee ID and the photo ID. So this is compounding proofs, and I could keep adding them as my policies demand for more. And that takes me to the fourth and the last demonstration here today, which is of predicates. So for each one of these data attributes, I have the ability to add a predicate function. So with the employee ID here, and it doesn't make much sense for the use case I'm describing here, but I think you'll understand the concept. I have the ability to add a function to it. So maybe I want the employee ID to be bigger than a certain amount. And let's say that number is 10. I could specify that in here. So I have the ability here to add different functions to the attributes to specify if I want values to be greater or lesser than, that type of thing. So this summarizes the 4 different privacy preserving mechanisms that we've implemented in our instant task function within Orbit Enterprise. The concept of restrictions, which I've been able to set, the concept of data minimization by only selecting data that I really require to be shared with me, the ability to compound proofs, and then the ability to add predicates on specific data attributes.